Okay, last time we talked about the moving average, and the moving average was just an average of previous periods, excuse me, divided by the total number of periods. This was pretty straightforward and pretty easy. We did this example in class, and we looked at just previous demand for those previous months. And then given that, we just added up the previous 4 months, and that was given 4 months, divided by the number 4, because it was 4 months that were observed, and then get the answer. So for November, we said it was 178 pallets. For December, we said it was 181 pallets. Again, for December, we went 4 months back, including November, October, September, and August. And then we went to weighted moving average. So instead of dividing every previous month as the same weight, we did the weighting moving average. And the weighting moving average was putting weights or A's or alphas in front of every single term times the previous demands. And again, similar to last time, we did November and December, except this time we had the weights given to us. So 0.7, 0.2, 0.1 for a 3-month weighted moving average. And then again, for December too, we used the November data to get the December forecast. And then we did the statistical forecasting for exponential smoothing. Exponential smoothing, we can use either equation that's on the screen. We use the first one. And we said that there are 2 parts to the equation. The first part is what is the alpha times the demand, which we have no control over. The customer controls that. Plus 1 minus the alpha, which is the weight for the forecast. If we feel that our forecasting is pretty good, we want that 1 minus alpha to be pretty big. And therefore, the alpha should be small. So that weight of 1 minus alpha should be big, or can be big. And if the alpha is small, that means our demand will be small. The randomness. But if we feel that we are not good at forecasting, it's probably better to have it reversed. Have the alpha be big, have the forecast weight be small, and therefore put more emphasis on the demand than in the forecast. And then here's the problem that we were trying to go over last time, but I did not show you just because I didn't have the right connection for my laptop. But here's an example of exponential smoothing. Notice that the smoothing factor is 0.25. That's our alpha, which means the complement, the forecasting side, is 0.75. That means there's more weight on the forecast than there is on the demand. So note that we have 11 weeks of data and we're trying to figure out the forecast for week 12. Note that also the forecast has been built up off of each previous forecast week, right? So it's used this exponential smoothing equation for each one. So you can see in demand, we're looking at 73 for week 1, 68 for week 2, 82 for week 3, 78 for week 4, 81 for week 5, and so on and so forth. There's a lot of variation. Note for the forecast, there's not a lot of variation. Again, it's smoothed out because of that coefficient. So 73, 73, 72, 74, 75, 77. It moves, but it moves much more slowly than the demand does. The demand is much more sporadic. And again, because we have no control over the demand, but we can control the forecast. So the question is, what's the forecast for week 12? Well, it's pretty easy just to put the numbers into the equation. So the forecast for week 12 is the alpha times the demand for week 11 plus 1 minus the alpha times the forecast for week 11. And we know what those are. The forecast is 0.25 plus 89. That was the demand for the previous week. Plus 1 minus the alpha, 0.75, times 84. That was the forecast for the previous week. And we have 85.25. And here I rounded down, 85. Again, normally, I think I did that when I made these slides. Normally, I would round up. So if you round up or down, it doesn't matter, right? Probably always better to have a little bit more than a little bit less, but still. So week 12 is going to be 85, just for this example. So we know that the forecast for week 12 is 85. What's the forecast? I'm sorry, what's the demand for week 12? So if we have a forecast of 85, what's the demand for week 12? How do we calculate the demand? And it's a classic great trick question. The answer is we don't. We don't know what the demand for week 12 is. It hasn't happened yet. We're forecasting from week 11 into week 12. Who controls the demand? The customer does. I have no idea how many pallets or how many washing machines, whatever it is we're selling, is sold for week 12 because we're not there yet. We'll find out at the end of next week. And then we can compare to see how well our forecast was compared to the demand. Now, from our example, if you look at week 1, that's what we want. excuse me, we want 73 for the demand and 73 for the forecast. We nailed it. We sold exactly how many washing machines we had planned. But then notice for week 2, the demand is 68 and the forecast was 73. We actually over forecasted. We ordered too many and we didn't sell nearly as much, which means we have leftovers. We have 5 units that are left over that we didn't sell. Note for week 3, it's the reverse. We under forecasted. The demand was much higher than the forecast we had anticipated. So we could sell those 5 extra washing machines from week 2 to help eliminate some of that gap between 82 and 72. But we still under forecasted. We still have 5 units we couldn't sell. It's missed opportunity. We could have had that opportunity. So again, we're trying to make it as close as possible. So the question is, now back to the alpha, that smoothing factor. Are we good at forecasting or not? And I think I drew on the board, or maybe I didn't, but if you look at the screen right here, you can see that the demand is in red, the lighter red, and the forecast is in the brownish color, that darker red. And you can see that almost every time the demand is higher. So is our forecast good enough? I mean, it's up to you. We'll figure that out in just a moment. But notice that because of that demand is always higher, we are under forecasting. The forecast is always less, or almost always less than the demand, right? And that's a problem. So we could argue that our forecast isn't as good, but again, we'll figure that out in just a little bit. So let's assume that our forecast is not good. Is alpha the right number? And that's a great exam question. Is 0.25 appropriate? Well, 0.25 means that our demand amount is small. That's our weight for demand. Now, our 1 minus alpha is 0.75 times the forecast. If our forecast isn't very good, should we have our weight for that forecast be 0.75? And the answer is probably not, right? We probably should just, if we're not good at forecasting, we should probably have a higher alpha and therefore put more weight on the demand instead of the forecast. But right now, I want you to realize that there is a under forecast and over forecast, and we're kind of judging how good the forecast is. And we don't know what the demand for week 12 is because we haven't experienced week 12 yet. Okay, any questions on that? Again, there are practice problems on Moodle. Go ahead and take a look at them. This will help you for the exam. Okay, last thing we're going to do is regression analysis. Now, brush up on your Math 224, brush up on your Math through Business 150 or 131. This is something that for one of those classes I'm sure that you cover, is regression analysis. This is statistics in its purest form. This is statistics that can be challenging for people. So I'm recording this video, I'll post it on YouTube. Feel free to look at this again. I'm not going to have you do the regression analysis. Instead, I'm going to have you interpret it and understand how to interpret a regression. And I've decided to use a real problem. So an actual problem that will help you understand regression a little bit. What it does is it takes a bunch of variables. We call them independent variables, a bunch of causes. And we're looking to see an effect. And then in regression analysis, we only have one effect. So what is that one thing, that one feature we're trying to analyze? And we're trying to figure out what are all the causes. For example, why do people vote the way they do? Could be their socioeconomic status, could be the culture of the state they live in, could be the amount of income that they make, it could be their family preference on they vote Democratic or Republican or independent, etc. All of these are independent variables that are leading to a y variable or dependent, which is why do I vote the way that I do? Okay. Here's what it looks like. Here's an example. It's the y equals mx, or the line equation, the equation of a line again. So for an example, a sales forecast for a company is going to be based on the base sales, which is just generic. It's called the y-intercept. It's a constant number, and it happens to be, practically speaking, it's what we always make. It's the minimum of what we always make. Let's say a sales forecast is about 2 million a year, and so that's our capital B. Then the lowercase b's are weights. And the weights are going to be calculated with how well, when we graph all these points on a line, how closely do they stick to the line? How close, if we had to draw a straight line, are they on the line? Are they close to the line, etc.? These weights are created there. Now, where do the points come from? Well, this is the data that we collected on these 4 other variables. D is disposable personal income, A is advertising expenditures, F is fuel prices, and S is sales from last year. So if we can plug all those in, we can put in data points and see, can we create a line where we can predict the sales forecast for the year 2020, or maybe 2021. Okay. Now there's something important to the equation, and that is once you create an equation, once you figure out what that equation is, you can use it. Which means if you want to randomly try in different values or different variables for these capital letters, you can create it and see what your sales forecast will be, your dependent variable. And that's important because, as you'll see, that really provides us a lot of forecasting ability. So, what's the example? Well, our family are big Dairy Queen people, so we typically will go to Dairy Queen. I don't know, in the summer, maybe once a week, maybe once every other week, somewhere in there. So imagine we go to a Dairy Queen in Franklin, okay, not far from the school. I'm 31. And what we do is we go in and say, somewhere in the summer, hey, the question is, how many days does the average person go to Dairy Queen per week? So what we'll do is we'll stand outside the Dairy Queen and we'll say to every customer that's coming in, that goes up to the drive-through, here's what we'll do. We will pay $5 towards your meal, towards your order for ice cream, provided you give us some data that we can look at. So we're just randomly going up to a bunch of people, about 35 people, and asking them, we'll pay for your ice cream as long as you help us with data on a survey. Can you fill out a survey for us? And a good number of people say yes, because they want free ice cream. And so what we do is when we get that data, we ask certain questions. For example, the first one is, what is the average temperature? Translation, do we feel that the temperature influences the amount of times somebody gets ice cream per week? Second, is ice cream expensive? This is your perspective on ice cream is something I can get often or not. So this is, a psychology question. They put in a 1 if it's not very expensive. They put in a 3 if it's very expensive. If it's somewhat expensive, they put a 2. Number 3, what is your age? Do kids eat more ice cream than adults? Do the elderly eat more ice cream than adults? Do the elderly eat more ice cream than kids? We don't know. But let's put in the person's age if they're willing to give it to us and then see if that has any influence on how many times they have ice cream per week. Question number 4, what's your income? Put in a 1 if you make less than $30,000 a year. Put in 2 if you make between $30,000 and $60,000 a year. And 3 beyond $60,000. Translation, if your income is higher, does that mean you're more likely to buy ice cream? Now notice how similar that is to the previous question, is ice cream expensive? But now we're putting a dollar value to it, a monetary value. And then 5, are you healthy enough to eat ice cream? So 1, yeah, I'm very healthy. It doesn't bother me. Number 3, I put a 3 if I have diabetes or I have a sugar intake issue. And I probably shouldn't be eating ice cream, but I'm going to anyway. So I'm just guessing from research. These are 5 questions that will help influence and explain why people get ice cream so many days per week. And we ask so many passengers in their cars, and this is what we get. We find that the first column is how many days per week they get ice cream on average. The second column is the temperature for the day. That's my first independent variable. The second variable is the cost. Is it expensive or not to us? The third is the age of the person. The fourth is the income. So do they have low income or high income? And then the fifth is, are you healthy enough? So note that this person, the 5 down on this chart, is 16 years old. Ice cream is pretty expensive. I mean, it's not something they can do. You have to spend allowance to pay for it, or maybe have the parents pay for it. Income is pretty low. It's less than 30,000. And 3, they're not particularly healthy. Maybe it's an overweight child, or maybe their parents have influenced them. You shouldn't eat ice cream a lot. It happens to be 72 degrees that day. Notice as we get to the bottom, the fourth from the bottom, 1, 2, 3, 4, the person is 76 years old. 3, income is not an issue. They make over 60,000 and it's not very expensive. It is 93 degrees and they are not healthy, which means that they're sneaking out of the house and they eat ice cream 3 times per week. This is somebody who's decided, I'm toward the end of my life, I don't care anymore. So we get all kinds of data from all kinds of people. And this is our data. And what we're going to do is we're going to put it into Excel and create a regression analysis. In other words, how many of these variables really influence the ice cream consumption per week? Does everybody understand that? Any questions? Any comments? Okay. So let's go to the next one. Here's our model. The amount of ice cream per week equals a beta naught, which is a weight. Again, that's that constant. Plus another weight, beta 1, we don't know what it is, times the temperature for the day, plus a beta 2 times the cost, 1 through 3, is it expensive or not? Plus a beta 3 times the age, plus beta 4 times the income, 1 through 3, again, less than 3,000 or greater than 3,000, plus beta 5, what is my health, plus an error term. And an error term just means that here's a number or an output that comes out because not all the lines not all the data points are going to fall on a straight line. So there's that variation, the variability. And here's what we're going to do. One, we're going to run the results. So we're going to plug it into Excel. It's going to create an output for us. Number two, we're going to check something called an F test, maybe a Fourier test. Nobody really remembers what F stands for. But the question of the F test is there anything really here? Are these variables actually linked together? Is there a correlation, or is it just nonsense? If it's nonsense, just shut it down and say, you know what, we're done with this problem. There's no explanation. But if the F test is pretty high, which is greater than 5, or the p-value is less than 0.05, then we're doing pretty well. There's some sort of explanation between the y variables and these x variables, the y variable and x variables. The third thing is check the adjusted r squared value. In other words, how much of the y is explained by these independent variables? So how much of ice cream consumption per week is explained by these 5 variables? Number 4, check the p-values of the x variables. In other words, now I'm going to throw out some of these x values. And the criterion is it less than, is the p-value, the percentage value, less than 0.05? And then finally, keep only the variables that should stay in the equation. In other words, keep the variables that have p-values less than 0.05. Now, why do we do 0.05? 0.05 is needed because we're assuming with 95% confidence that this is correct, or that our data is correct. Remember, we could pull up a whole 50 new people for the next day and get different results because different people behave differently. But what we're trying to figure out is with 95% confidence, we can say, given any sample of 40 people, this is what we'll find. And that's why our p-values have to be less than 0.05. It says that with 95% confidence, or 0.95 as our probability, everybody behaves this way. And so that's why we have that variation that's there. Okay, so let's actually look at the data, the results, and try to figure it out. This is an example of an Excel output. And so the first thing we're going to do is, again, check that F test. Now you can see that in the middle. It's called an ANOVA, an analysis of variance. Degrees of freedom and error terms, etc. And then at the far right of that middle table says F. And as a rule of thumb, F has to be greater than 5. But more importantly, the significance, or the p-value of F, should be less than 0.05. And you can see right here that the F is actually 30. It's greater than 5. And the significance of F is 3.512 times 10 to the minus 8th. In other words, it's really, really small, less than 0.05. So what does that tell us? Significance F, there's actually something going on here. The amount of ice cream consumption per week is explained by at least one of these variables, maybe more. And that's our point of the F test, to make sure that there's some connection between the y variable, consumption of ice cream, and these x variables. If there was not, if it was greater than 0.05, if it was less than a value of 5 for the F test, chances are we can just throw it away. There's nothing here really makes any sense. It doesn't explain anything. Okay, second thing, we said we had to look at the adjusted r squared. That's actually up at the top. And notice there's an r squared and an adjusted r squared. So what's that all about? Well, r squared is called the coefficient of determination. It tells us that there is some relationship between y and x, much like the F test, except this explains how much, what percentage of the y is explained by the x's. In other words, what percentage of the ice cream consumption per week is explained by the x variables. And in this case, we use the adjusted r squared, not the r squared. And here's why. Statistically speaking, the r squared shows correlations. So we keep adding correlations and evaluating correlations between the y and each individual x. The r squared, numerically, every time we add a new variable, it always increases. So if we had 10 variables, it would be even higher. If we had 20 variables, it'd be even higher. The adjusted r squared actually penalizes the data because it only adds correlations because there's a significant explanation between them. In other words, the x variable actually explains the y variable really well. And it doesn't just artificially increase the number for every additional x variable. So we always want the adjusted r squared. And you can see here from the circled area, adjusted r squared is 0.864. In other words, that's 86.4%. That's huge. 86.4% of the number of ice cream visits per week per person is explained by some of these variables. That's a lot. In other words, the data points that would show up on a graph tend to form somewhat of a line, a trend, a straight line. So a lot of these data points are either close or on the line. So know what your adjusted R-squared are. It's the percentage of the y that's being explained by the x's. Okay, third thing, let's look at the individual p-values. Here are all of our different variables on the bottom. And the first column is the coefficient. Those are those weights, those are those betas that we looked at before. Notice the first beta is minus 5.039. That's going to stay constant. And as we look at the p-value, you can see it's less than 0.05. So here's my p-value right here. My p-value for the intercept is 1.96 times 10 to the minus fifth. My p-value for temperature, the next variable, is 9.37 times 10 to the minus ninth. Again, really small. Now look at the other four. Do I feel the ice cream is expensive? Well, that's 0.31. That's greater than 0.05. Do I feel my age is important? That's 0.38. Does my income matter? Well, that's 0.76. Does my health matter? That's 0.77. That's even worse. So translation, I can get rid of these bottom four variables. They don't really add anything to the adjusted R-squared. They don't really add anything to my y value, my y values. And so when we write the equation, there's only two variables. There's our intercept and our temperature. Those are the only things that we keep, because we can say with 95% confidence they are always going to be involved. They're always going to be variables that will help explain why people go get ice cream every week. So we'll put them into equation. We'll take the coefficient and then we'll multiply it by the variable. So our equation is going to be minus 5.039. That's the first column in that table for the intercept, plus 0.081 times whatever the temperature is, plus an error term. Now here's another way you want to take a look at it. If you look at the coefficient, not the coefficient, if you look at the confidence interval, look at the last two columns of this table. Notice for the y-intercept, or the intercept up front, notice the lower 95% confidence is minus 6.88, and then the upper 95% is minus 3.19. Just a quick check and a quick rule of thumb. If you ever cross the zero, then you know that it can be thrown out. It's less than 0.05. Look at the temperature. It's 0.064 and then 0.098. We never cross the zero. It never goes from negative to positive or positive to negative. But now if you look at the other four variables, minus 0.124 to 0.368, we cross the zero. Again, age, minus 0.098, which is really close to zero, and then positive 0.24, we cross the zero. And the same for the bottom two as well. So if you want a quick check, just knowing statistically, if it crosses zero at any point on that lower and upper 95% confidence, then it means you can throw it out. If it doesn't, you should keep it. But primarily, you should just look at the p-values. I think that's easier. So let me write my equation. This was my long equation, my original one. And now, based on the weights that I have and based on the data that I looked at, this is my equation. Now think about this from a forecasting perspective. Look how awesome this is. Look how short it is. It says, if I can predict my temperature, I get a feeling for the week how many people are going to come get ice cream, which means I can forecast how many 5-gallon tubs of ice cream I need at my Dairy Queen location. And Dairy Queen is soft serve, right? So it's a lot even easier. It's just chocolate and vanilla. So for example, if the temperature is going to be 75 degrees, I can assume that the average person is going to come to Dairy Queen once a week, 0.96 times. But if the temperature goes up to 95 degrees, I can assume that the average family will come 2.56 times, or almost 3, somewhere between 2 and 3. And I can schedule how many tubs of 5-gallon ice creams I need based on that. So once I have an equation, boy, that makes life a lot easier. I can just figure out, plug everything into the equation and figure out on average what my y would be. And again, this is a linear equation that we're looking at based on the data that we collated. Now this is regression, and I've gone through this pretty quickly, right? Hopefully it makes sense. Hopefully you understand a little bit of this from previous classes, but this is the regression equation. And there is, I believe there is one on Moodle you can go through and do a practice problem. Before I continue on, are there any questions on this? In the chat or on microphone? Okay. Okay. So a couple last things, and if we need to go into Monday, we will. But a couple last things after this. We're not going to do simulation models focus forecasting and simulations. But what I do want to do is go back to that exponential smoothing and say, how good is my forecast? Really, how good is the forecast? And we'll go over this again, since we're running out of time. We'll go over this again on Monday. But there are 3 different equations that will tie together and make you realize how good your forecast is. Okay, this is also on the exam. The first one is called bias, and the equation looks challenging. It's got a sigma in there for standard for summation. You're going to subtract the demand minus the forecast and divide by the number of forecast periods. This is easy. It's just taking the average. So notice we filled in. We still have our equation, our information from the exponential smoothing equation. This is our problem from before. And I assume that at the end of week 12, we actually sold 82 washing machines. So we predicted 85, but we sold 82. So we over forecasted. The forecast was greater than demand. And notice I'm subtracting, for this problem, I'm going to subtract the demand from the forecast. Okay, so the top line from the bottom row. So what I'm going to do is I'm going to calculate the error for each period. In other words, how good am I at forecasting? What's my bias? And I'm asking the question in bias, am I typically under forecasting or over forecasting? Well, we know from our graph that we're typically under forecasting. So if you look at the demand minus the forecast, you can figure out for each week, here's what I'm looking at. So week 3, I under forecasted 82 minus 72 or 10 washing machines. For week 4, I under forecasted 4 washing machines. For week 5, I under forecasted 6 washing machines. For week 6, I over forecasted 1 washing machine, which was not so bad. But then week 7, I messed up again. Now I'm at 10 under, right? Notice the weird thing about this. When we subtract the demand from the forecast, a negative number means that we over forecasted. And a positive number means we under forecasted. Now that's counterintuitive, but that's just the way the equation works. So what I'm going to do is I'm going to take all these errors for 12 weeks. I'm going to add them up, and then I'm going to divide by 12 because I'm looking at 12 periods. So here you go. So I add them all together. It ends up being 46. And then I divide by 12, or 3.84. Translation, we underestimate regularly, because it's a positive number, by about 4 pallets per week, or 4 washing machines per week. That's my bias. So every time I place a forecast with this exponential smoothing, I typically am under forecasting, which means I either need to add a fudge factor at the end, which is, well, let's see, I'm expecting 85 washing machines for the week. Let's add 5 to that, or let's add 10 to that, so that we're not under forecasting. So that's my fudge factor. Or I need to find a different way to be have a more accurate forecast. So that's this idea of bias. Now we're going to continue to walk through bias and go through absolute deviation and percentage error starting on Monday. But since I'm out of time, I'm going to stop here. Okay. But note that this is how you can do bias. And all we're doing is subtracting the demand from the forecast for every week. We could have done this for the months prior with the moving average or the weighting moving average, etc. This doesn't really work for regression. So here, know what that is. And all we're doing is looking at the errors, subtract the demand minus the forecast for every week, and then add them up, divide by the number of periods, the number of weeks. So I'm looking at 3.84, or about 4 pallets per week, 4 washing machines per week. Okay, any questions at this point? If there are none, again, this video will go up on YouTube in just a few moments. You can take a look at this. This is not for exam 2, it's for exam 3, but you should know it. And when you get the chance, go through the material that's on Moodle, the practice problems, and figure that out. We will continue this starting on Monday. So it is now 8:38. Well, it's a couple minutes past 8:35. Thank you very much for joining us. I'm going to stop the video now